Hi everyone and welcome to this session of ACM Goa Talk. I'm happy to announce that we are starting a new term in the ACM Goa chapter, professional chapter, and we plan to host monthly expert talks, research talks, and introductory talks by experts, which are online and open to all. And we also plan to have an offline event somewhere in September timeframe, which would be like a networking event for researchers in Goa. So looking forward to seeing you all at the networking event. I'm very happy to welcome our speaker, Mr. Ayush Chopra here. And let me introduce him. So Ayush is a PhD student at the MIT Media Lab, supervised by Professor Ramesh Raskar. His research lies at the intersection of agent-based modeling, distributed machine learning, and privacy, with the goal of harnessing collective intelligence to guide population-level decision-making. His research has resulted in papers in top-tier AI conferences and interdisciplinary journals such as the AAMAS, KDD, CVPR, ECCV, Informs, and so on, and Best Paper Awards at CVPR and ICML workshops. His projects have resulted in 25 patents and have been featured by Reuters, Weather Channel, VentureBeat, etc. Outside MIT, Ayush is affiliated with the Mayo Department of Epidemiology and has spent time at JP Morgan AI Research. Prior to MIT, Ayush was a researcher at Adobe, where he focused on advancing in-browser computer vision and machine learning, and also received the Adobe Outstanding Young Engineer Award 2020. Ayush co-organized the ICLR 2021 workshop on distributed and private machine learning and the ICLR 2023 workshop on AI for agent-based models. Ayush received his SM degree from MIT in 2022 and BE from Delhi College of Engineering, India in 2018. So thanks for joining us today, Ayush. Over to you.
Hi, can you hear me?
Yeah, you're audible.
Hi, Neha. Thanks for the introduction. Hi, so I'm Ayush. I'm a PhD student at MIT, and I'll be talking about my research on learning to simulate populations with millions of agents. And the motivating premise for this research is that LLMs are all the hype today. How do you think of generative models, decision making, behavior understanding in a world beyond LLM? And consider, for instance, this motivating example I want to start with. During the COVID-19 pandemic, testing was an important intervention used to mitigate the spread of an infection. Consider, for instance, I ask you this question: what kind of a COVID test do you want? As an individual, you want the most accurate COVID test. If you're infected, you want to know. If you're not, you would much rather not quarantine. So for an individual, the incentive is I want a test that is highest, that's most accurate or most specific, to be even more precise. However, when the government is trying to make a similar decision for a population, their metrics and incentives change. They're not trying to necessarily protect a single individual in the population, but their metric is to reduce the total number of infections in the population. In that scenario, for instance, they need to think about both. They don't just need to think about the properties of the test, the specificity, the turnaround time, and the quality of the test, whether it's an RT-PCR test or an antigen test. They also need to think about the properties of the population. People move around, infect each other. So an understanding of the population behavior, the demographic, geographical distribution of the population is an important characteristic. For instance, in this scenario, we realized that the turnaround time of a test result can be more important than the accuracy of a test. If you're trying to protect an individual, you want the most specific or the most accurate test. However, if you're trying to protect the population at large, maybe you want to pick a faster test over a more accurate test. This is like one of the many examples where we realize, and this is one of the reasons why rapid point of care tests and rapid antigen tests became extremely popular during the second half of the pandemic. So this is one of the many examples where we realize that population level outcomes can be non-intuitive and non-obvious due to complex individual interactions. And what's good for an individual may not always be optimal for a population. So the overarching goal of my research is to build generative tools that can help us evaluate such questions where we need to jointly consider some properties of an intervention and the properties of a large population, and build these tools entirely in simulation so that you can understand, analyze, and intervene upon populations with millions of agents, and trying to make this as realistic as possible. So we've been extending our research into a lot of applications, and I would like to give you a broad spectrum of some of the applications we worked on, especially in context of the COVID-19 pandemic. So you can use these tools to ask a lot of questions. So one of the papers we wrote early on during the pandemic was, what if we delay second dose of the COVID-19 vaccine? So in the beginning of the pandemic, this is the pre-vaccine era where we're trying to figure out, given that we finally have a vaccine, how best do you immunize a large population? As we've realized during COVID, immunization, the process of distributing a vaccine to a large population, is actually much more complex than actually just building a vaccine. For instance, we need to consider supply chain limitations, population behavior. People don't want to take a vaccine or cannot afford to, may have other comorbidities, to design immunization policies. So when you've got limited doses, we wanted to ask more prospective questions and evaluate prospective interventions. And for instance, in one of our research, we showed that you could actually delay second dose of the COVID vaccine under certain constraints on effectiveness of the first dose and a combination of other properties. And this a similar policy was adopted by the UK government, which helped save like 10,000 lives, 58,000 hospitalizations during the peak of the pandemic. And we were one of the groups they consulted with. And you can also use these tools to ask really good retrospective questions. Like in retrospect, we could say that delaying second dose was a really good policy, but based on this post hoc analysis by a different institution. You could actually do retrospective analyses inside a simulation as well. So during the initial phase of the pandemic, lockdowns were the dominant policy that was used everywhere. So one of the ways to know if a lockdown is really effective is something called a seroprevalence study. So what a seroprevalence study really does is you go to the population, collect a lot of blood samples, do antibody tests to see, does this person have antibodies against this infection? If you do that, you'll know who really got infected. So it's a very effective strategy, but very expensive. You need to go to the field, do real trials, and collect data. So using our simulators, because they work at real world scale, you can reproduce trends of seroprevalence studies entirely in simulation. So you can use this to guide better seroprevalence studies, do better A/B trials, analyze retrospective decisions, to in a way also prepare better for the future. We could also ask questions like, what could we have done differently? So that you can like design counterfactual policies with multiple constraints entirely in simulation. So all these kinds of scenario analysis, asking what if questions, what really happened, what could we have done differently? This is the general flavor of questions we can ask with these tools. For instance, here, we realized that lockdowns were really good during COVID, but extremely restrictive, and they've had a really bad impact on the economy since. So maybe we want to ask questions like, what could we have done differently? Could we have designed lockdown policies which had an equivalent public health impact, but were much better for the economy? So in retrospect, our simulators allow you to ask these questions so that you can understand the past, improve the present, and plan better for the future. So what we really need to answer these questions are, we need generative models which can do domain-specific scenario analysis. So our models need to have scientific accuracy, because most of these models need to encode the right mechanism to simulate. For instance, when you're trying to simulate the spread of an infection, you really need to understand how does the properties of the variant interact with the comorbidity of a population. Does it vary with age or with gender, with demographics? We want to model the behavior of an individual population. Usually these are problems with very sparse data. You don't have like millions and billions of data points to train really large models on. These are rapidly evolving problems, so there is a lot of domain shift always happening. And since these tools are to be used for real large-scale decision-making, you want interpretability and you want your simulators to give you quantitative results. So this is the motivation behind our research, where we want to introduce and build on top of the concept of ABMs, which are agent-based models, and not LLMs, to build co-pilots for such policy decisions. For instance, this is just like an example that I quickly went to ChatGPT and tried to give it a similar prompt. And ChatGPT can be good for doing more general purpose scenario analysis and decision making and recommendations where you don't really need domain expertise. But in these problems, as you can see, the response is really verbose and isn't really grounded in understanding of the specific problem that we're tackling. So maybe we need to think beyond. And that's the motivation of this research, that how do you do generative modeling beyond large language models? And I want to motivate ABMs as the alternate to do more domain-specific decision making. So agent-based models are like a general class of tools to simulate heterogeneous populations. They simulate the bottom-up interactions and actions of multiple agents in a population and generate population-level effects. I know this sentence is very verbose, but it'll get clear as we move on. But agent-based modeling is a really old discipline, and it's extremely interesting because it's relevant across disciplines. So an agent-based model is basically a lot of agents that interact with each other and influence each other, and interesting things happen at the population due to simple interactions between agents at the local level. This is relevant across digital, biological, physical realms. These agents could be cells in a tumor microenvironment. They can be humans in a physical environment spreading infection, or they can even be like AI avatars and humans in a digital environment spreading information and influence. So it's a very general purpose concept, and it's been around for a long time. So ABMs have been built for a long time, but conventional ABMs have been very slow to execute, difficult to scale, and very tough to calibrate to real-world data. For example, a bunch of old agent-based modeling platforms, if somebody familiar with the field might have heard of things like Mesa, Netlog are really popular, simple Python-based agent-based modeling platforms, but they've been very difficult. They're very slow conventionally. They'll take like hours and hours to simulate a really small population of like 1,000 people. And they don't scale to like real world populations, so you can't really do decision making for the real world. And it's tough to integrate real data with them. Some people have done efforts to like provide scale and speed, but it doesn't really work. And all of these ideas are like way far behind in the past. And what we really need are ABMs that can recreate million scale populations with detail, integrate with real world data streams, and give you a tool to analyze sensitivity of results, since you want to make high risk decision making with these tools. And that's roughly the motivation for our research. And the key insight we'll exploit throughout the research is how can we benefit from all of the modern advances in automatic differentiation with all the great infrastructure and tooling that's been built to rethink ABMs in this AI first world, so that can we build more scalable and differentiable agent-based models that basically execute on compute graphs, are more compatible with modern automatic differentiation, and can leverage and benefit from all of the advancements in computation and analysis that have happened over the last 10 years with the deep learning revolution. So all of the ideas that I talk about in this research have been done in collaboration with a group of researchers across a variety of institutions in academia, industry, and in policymaking. And yeah, I just wanted to share the slide. This work is with the collaboration of several people. Oh, yeah, I see. Okay, I had a question. Also, I'll talk about differentiable in more detail, but as I get through the slides, but differentiable means, so these are simulators which have a lot of input parameters. You simulate a mechanism, you get an output. And what we basically want is that at any step, I should be able to take the partial derivative of any output metric with respect to an input parameter. For instance, if the model is simulating an infectious disease, let's say an input parameter is I want to know the R naught of a virus. That's the input. And the output is any metric I log. Maybe it's the total number of infections. So I should be able to, let's say, do DI by DR naught at any step. Does that sort of answer the question? I'll talk about this in like a lot of detail. Yep. Okay. Before that, I just wanted to give a brief background about me. So I'm a PhD candidate at the MIT Media Lab. My background is primarily in machine learning, solving AI and inverse problems, specifically for imaging and increasing ABMs. Before grad school, I helped start a company where we were building a platform to work remotely. So doing a lot of computer graphics and computational imaging is my background. So we built like video streaming platforms to deliver better group presentations where you could basically co-browse, share browsers. I spent a few years at Adobe, where I tried to, again, work at the intersection of machine learning and simulations, specifically trying to simulate light to build tools like what if you could try on clothes in the browser. And I initially started grad school to build more AI compatible differentiable rendering, where you could bridge machine learning and modern advancements in computation with simulators of light so that we could go beyond the visible spectrum and go beyond what we can see. And I'm doing my PhD at this group at MIT called the Camera Culture Group, which specializes in these tools. And like the group has built tools that can look around corners, tools to see through fog. And we've been working with simulators of light for a really long time and trying to improve rendering and the ability to just manipulate light signals. And increasingly, I, as you can observe, did a major pivot. I don't really work with imaging anymore, but a lot of those insights actively guide my research. And the motivation is that can all these advancements in AI, machine learning, and imaging help us advance agent-based simulations? Okay. So what we basically introduce are this concept called a GradABM, not an ABM, where in a very like canonical sense, the intuition is can we take the grad of an entire agent-based model, which basically can we take the first derivative of a model. And the key insight is we want to build more tensorized and functional simulators so that we have really fast forward simulations and differentiable inverse simulations. And I'll show that these simulators scale to realistic populations. You can go to millions of agents. A big aspect when you run simulations is simulators have a lot of parameters and you want to calibrate them. So one of the new things this unlocks is that you can calibrate parameters using automatic differentiation and also integrate with deep neural networks while keeping your simulators entirely mechanistic and interpretable. And this allows us to learn really personalized, robust parameters and also do uncertainty estimation. And one of the other big things is that you can actually do a lot of validation and sensitivity analysis on these simulators without running any simulations, using like all the gradient and Hessian information that's available now in a differentiable simulator. And finally, these tools enable a lot of digital experimentation and strategy design to ask questions about the future, like what if we delay the second dose, and analyze decisions from the past, like what really happened, how effective lockdowns really were, for instance. Okay, to give you some performance benchmarking, GradABMs have really helped advance performance in a bunch of simulations. For instance, this is like performance on, this is one popular epidemiological model called June, which is actively used in the UK for a lot of decision making. Conventionally, like June is implemented as a simple Python agent-based model like Mesa and a bunch of these other frameworks. And so we started working with them and we re-implemented June as a GradABM, not an ABM. And now you can massively accelerate the time for simulation, calibration, and even decision making. And you can effectively scale simulators to entire countries and run it very seamlessly on a GPU. So these are results from running on like a simple 20 GB GPU that is available in most labs these days and trying to simulate all of London with like 8 million people. And you can get massive benefits in performance, which can unlock a lot of downstream decision-making benefits. Okay, for the context of this presentation, I'll try to talk about the design principles of GradABM in the context of an epidemiology problem. And towards the end, but I'll also talk about this framework we've built called AgentTorch, which allows us to generalize these ideas to arbitrary domains. And AgentTorch has a PyTorch as an API built on top of PyTorch, which you can use to specify your own agent-based models. Yeah. Okay. So before moving on, let me give you a brief representation of the kind of simulator we have. So our simulators have a lot of agents. So agents in this case are like individuals that get infected and spread infections. So each agent has a state, which is represented by a bunch of properties. The state usually has like type variables, which are properties which do not change through the simulation, like the age, occupation, household of an agent. And they also have like context variables, which will evolve through the simulation as the agents interact with other agents. So you want to track like the disease status, the quarantine status, the vaccination status of agents. In these simulators, you can model extremely realistic and diverse scenarios of interaction. You can model like interactions between these agents inside a household network, at work, or randomly on the street, at a pub, at a game, all those kind of things. So you can use like really rich mobility data streams that are collected and used in the world these days to parameterize the interactions between agents in your population and do it for real populations. And throughout the simulation, the agent state continues to evolve. And you can model varying different kinds of mechanisms. Like agent state will involve when a new agent gets infected, the state of a previous agent continues to progress, and through a combination of interventions. So you can, in our simulators, you can test maybe like health interventions, like testing, vaccinations, lockdowns with extremely realistic setups. Like vaccination is 2 doses. There can be a specified delay between the first and second dose. Immunity can decay after the first dose. And you can also do financial interventions because they also tend to be really important during emergencies. And the entire challenge is, how do you simulate realistic dynamics and interventions, which have all the stochasticity, conditionals, and sparsity? For instance, if A and B meet, every interaction is stochastic. For example, if I meet someone, I may or may not transfer an infection to the other person. If the government asks me to take a test, it may or may not come back positive. So there is a lot of discrete stochasticity throughout the simulation. There are a lot of conditionals because at any point in the simulation, different agents are in different stages of their life cycle and journey. Some agents are going to take a test. Others just got a vaccine. Some just got infected. Some agents received a stimulus, money from the government, because they lost a job. Combination of things are happening. And there is a lot of sparsity. For instance, testing is happening every day of the simulation. Some or the other agents are getting tested. But stimulus payments, where like the government gives a one-time payment to all agents at discrete times during the simulation, is extremely sparse. Like things happen on very few days. So a lot of things are happening at different time scales with a lot of stochasticity, a lot of randomness. And the goal is, how do we model these entire things to as fully tensorized and functional operations that run exactly on GPUs and are differentiable. So one of the key insight has been that you want to build a tensorized and differentiable specification where we basically represent the agent state as vectors. We model their interaction environments as tensors. And the transitions, we sort of reparameterize to make sure that they're tensorized and differentiable. For instance, like a couple of the key motivating design principles are that you don't want to write if-else conditions, you want to write masks. So you can like just reformulate conditionals as masks. And you can actually reparameterize discrete distributions. Because if you sample from a discrete distribution, that's not differentiable. But if you, there's a lot of modern work where you can have like a smooth approximation of the gradient without changing the forward pass. You can do these things. And there are a lot of design principles for just building such an ABM that we talk about in the AgentTorch paper. And just for the interest of time, I would recommend you to look at just the documentation of the library. We've got like a huge helper support to implement a lot of these non-differentiable operations for use in simulations. But the key point I want to highlight is that this tensorization and specification is important because it leads to massive speed up. So the runtime scales linearly in the number of interactions. And it is also extremely essential to do any kind of automatic differentiation or iterative optimization. Because like automatic differentiation requires you to run multiple forward passes and optimize. And having a fast forward simulation is extremely essential. So as you can see here, we can scale to like x-axis then is like millions of interactions, and y-axis the number of time in seconds. So you can go to like maybe 5 million interactions in like 3 seconds. So you can scale to really extremely realistic populations. And this opens up a lot of interesting dimensions because we can run super forward passes, extremely fast simulations, and compute which are fully differentiable. So let me now walk you through what a calibration pipeline looks like and what calibration really means. First, any questions still here? Please feel free to ask any questions if you have, and then I'll move on. Okay, I'll move on to the next slide.
So I missed the starting few minutes. So can you tell me how ABM has an edge over other LLMs as compared to in these scenarios?
Oh yeah, I think there were like a couple of motivation slides at the beginning where, yeah, let me just quickly show you this slide. So they're meant for very different kinds of problems, but there are a lot of scenario analysis problems where what I'm trying to show is that ABMs can be better because in scenarios where you want scientific accuracy, you want to understand the behavior of a population, but you have very limited data. So you can't train a huge black box model, and you want interpretability in results, and you want quantitative outcomes. In these kinds of scenarios, when you want to build these generative models, you should much rather build like agent-based models rather than just black box large language models. And this is also a scenario where you cannot do things like reinforcement learning with human feedback and that stuff, because these problems don't have like a lot of data, like most domain expertise problems, like trying to understand infectious disease dynamics or trying to understand, I don't know, specific tumor microenvironments or decision making in a marketing enterprise. If you want to build like co-pilots for expert decision making, I feel the point I'm trying to argue for is think about ABMs, not LLMs. Yeah, does that give some context? I'm happy to share slides after and you can take a look.
Yes.
Yeah, okay. So the next thing we talk about is like largely calibration. So simulators have a lot of parameters. So this is like a simple demonstration of a simulation. You've got a lot of agents that are spreading some kind of an infection among each other. So every agent is in one of 5 states. An agent can be susceptible, exposed, infected, recovered, or in a dead state. So every blue agent is susceptible, red agents are infected with like a severe infection. Orange agents have like just got exposed and they're like infecting, but they have a mild infection. And black agents are in a mortality state and green agents are in a recovered state. So at every step of the simulation, there is transmission of infection amongst susceptible agents who also become infected. And there is a disease progression of already infected agents. For instance, this agent went from a susceptible to an exposed state because of its infected neighbor. This exposed agent developed a severe infection, and this infected agent unfortunately died. This is happening at every step of the simulation. And both of these operations are parameterized with a bunch of low dimensional discrete attributes. Let's say we call these parameters theta t and theta p, which are like parameters for transmission and progression. So these are not black box models. Both transmission and progression have some kind of a mechanistic understanding. Transmission maybe both, and they're coming from some kind of domain expertise in epidemiology, for instance, here. For example, theta t parameters can be the R naught of an infection, or like a combination, or basically the spread factor of a variant and like a combination of other variables. And progression can include things like mortality rate, the generation time of the virus, all those things which regulate how fast and how susceptible progression is. This will also like theta t will also increase like susceptibility by age, all these variables. So we run this simulation over k steps because we want to simulate like k days forward. And at the end of k days, what we get is like a histogram of aggregate predictions. We'll get something like how many agents are in each of these states. If we do this over historical days, what we also have is a lot of ground truth data coming from, let's say, the CDC, Center for Disease Control in the US, which is statistics on what happened in the past. And our goal is to estimate the parameters of the simulation so that we can simulate further and use it for decision making. Yes, k equal to 1 can mean 1 day. It's a one time step. So exactly, so the definition of a time step is up to you. It can mean 1 day, it can mean an hour, it can mean a week, it can mean a month, it can mean a year. It depends entirely on the kind of problem you're solving. But yeah, in case of this problem, k is 1 day. Yeah. So we simulate forward for k steps. And what we want is we want to estimate the parameters of the simulation, which basically best fit the predictions as compared to the ground truth. Now, this is different from having a black box neural network do it. Even if you're like trying to fit statistics, we would not have a black box neural network here, because what we eventually want is the ability to intervene on this mechanistic simulator, use the specific interpretable model that's been used throughout this description, and eventually we want to intervene on individual agents. So we can't just directly regress to the aggregate quantities. So because our simulator is fully differentiable and each step is, we can actually back propagate gradient through the simulator to compute a quantity. Like we can just do a gradient descent step on these parameters, where we can actually just optimize these parameters using the gradient of the loss that's computed between the aggregate predictions, which are y hat, and the ground truth case data, which is y. This is like the first mode in which you can calibrate these models, basically in parameter space using gradient descent. You can also, instead of doing that, because the pipeline is fully differentiable, instead of optimizing to scalar quantities, now you can actually have a neural network which gives you an opportunity to use a lot more auxiliary data sources which are relevant to the problem we are solving. This can be extremely multimodal auxiliary data, which is relevant to the problem we are solving, but cannot directly be incorporated in the simulation. For instance, this can be symptom surveys that Facebook are covering. Facebook is doing on its users. There's mobility data coming from Safecraft, which is a company which tracks mobility of people. There is the US Census, which gives you a lot of information about the spread of an infection, insurance claims, and all that information that's happening, and financial attributes, because that's a big driver of behavior. So now what you can do is, instead of directly predicting the parameters, use a lot of this multimodal discrete data, plug it into this neural network module, which predicts the parameters that are to be used for the simulation. And then instead of doing gradient descent on the simulation parameters, thetas, we actually do gradient descent on the parameters of the neural network, so that we iteratively update the neural network parameters so that it generates a new set of parameters that can better explain our simulation. And this is mode 2, where we can calibrate in function space using gradient-based learning, wherein we can have a lot of diverse data sources, which can help make our simulators more robust, push them into some kind of a neural network module, use that to predict parameters of the simulation, simulate case steps ahead. And based on the outputs of the simulator, we want to train this neural network so that it produces increasingly more relevant parameters. This is the second way you can calibrate this pipeline. So this is roughly what happens, that you can use a lot of heterogeneous data that is relevant to infection transmission and, let's say, disease progression here, but cannot be encapsulated into the assumption of the simulator. Use that to predict parameters. In step 2, you simulate case step of the simulation using the predicted parameters. In step 3, you get a prediction error between the computed aggregate statistics from the simulator and the real case data. And in step 4, you use a gradient of the loss via backpropagation to update these parameters. Now, this opens a lot of exciting possibilities to bridge AI and agent-based models. First, I'd like to note that calibrating using this process results in a pretty good fit and massive performance acceleration. For instance, this is basically calibrated to the first wave of COVID in the UK, which lasted from March to May of 2020. So black line is the true observed data. In blue is our calibration fit, which if you use this kind of a calibration pipeline, which takes roughly 12 hours on a CPU to calibrate for like the entire country, basically. And red line is instead of calibrating with our process, it's one of the most popular baselines that people use, where you use some kind of a Gaussian process to emulate your simulator and then try to calibrate. But trying to build such an emulator requires you to sample the simulator a lot, collect a lot of data, and it's increasingly very noisy. For instance, with the Gaussian process emulator, it took roughly 100,000 hours on a CPU to achieve this calibration fit. So there is definite benefit in the ability to leverage more data, can improve calibration quality, and also massively accelerate calibration time if you use some kind of gradient descent instead of trying to build emulator. And this also opens a lot of exciting possibilities where you can bridge machine learning and agent-based modeling in interesting ways. For instance, the thing about a lot of these domain-specific simulations, as I mentioned before, is that they tend to have very sparse data. So with one simulation, we have very little data. And so calibration tends to become very tough because you tend to underfit because you had so little data in the ground truth to fit against. So now what we can do is, because we've decoupled calibration from the main simulation process, we can jointly calibrate multiple simulators. So share weights of a calib-NN in like a multitask learning kind of pipeline that we've been doing in machine learning and deep learning for a while, where we have a shared calibration model that jointly predicts the parameters of multiple simulators. Let's say this is New York and Boston. Like we've got different models for the two scenarios. Both have limited data, but when we jointly optimize, we can get much better performance, and it helps improve calibration, reduce overfitting or underfitting for that matter. And you can also do other interesting things like maybe transfer learning. That let's say I calibrate on city 1, let's say I calibrate on Goa, and I want to transfer that model to Delhi. Previously, if I would just calibrate parameters, It's tough to transfer because you would give the parameters, but that's just an initial point. It doesn't transfer too much of the context of the infection dynamic. It's too low dimensional. But if you now want to do transfer learning, you can just give the weights of this calibration neural network instead of these simulation parameters. And that can help improve just bootstrap calibration in a newer scenario with much less data. So you can do things like multitask learning, transfer learning, meta learning, all the ideas that have really worked well in machine learning over the last few years. And you can, so this is like the third mode where you can jointly calibrate in function space. Function space meaning you calibrate a neural network to generate the parameters, not directly the parameters, and over multiple simulators in parallel. And all of these methods were like just estimating points, giving point estimates for the simulation parameters. You might also want to estimate entire posteriors over these parameters. And you can replace this neural network with something like a normalizing flow, which allows you to estimate entire posteriors over parameters instead of doing point estimates. Any questions till now? And there are a lot of other open, exciting possibilities that just exploring the space of possible calibrations of agent-based models by using advancements in modern deep learning, because you can differentiate through the simulator. I'll stop here for a minute. Any questions till now?
Yeah, one question. The simulator that you are using, is it particular or did you develop one yourself?
Oh, so basically, yeah. So in the sense, so the simulation platform is what we built, how to design the simulator, but we used a previous existing, sorry, I think I had a slide here. Yeah, so we actually, what the simulator we use is this thing called is June.
Okay.
So this is like a model that epidemiologists built and they're used actively in the UK.
Okay.
So the assumptions in the design of the simulator come from that, but we sort of re-implement it in our framework.
Oh, thanks.
Yeah. Okay. So, okay, if no questions, then I'll move on. So the next step is like, let's say you build a simulator, you've scaled it to like a really large million scale population. For instance, we're simulating all of London, like 8 million people, 3 million households here. And you've calibrated the simulator using a lot of diverse data and a bunch of interesting techniques. A big question is when you want to use simulators for real world decision making, you want to do some kind of validation before you can do decision making. Now, validation is important, and you'll have to do a combination of sensitivity analyses to know whether you've calibrated your model right. Does it actually represent the real world? Because there are a lot of possibilities which can fit to the same aggregate data. And this tends to be a huge challenge in simulation and is one of the most computationally intensive pieces of simulation. For instance, like sensitivity analysis is key. It's, for example, this is one scenario where in the UK, COVID sim was another really popular epidemiological model, and that was used for decision making. But before you can actually use these simulators, they wanted to evaluate the uncertainty of predictions on like assumptions of the simulator. So this simulator had 940 parameters, which are input to COVID sim. And the goal was, can we find, let's say, the 19 parameters that the output is most sensitive to? And to do this simulation, how will they do the sensitivity analysis? You'll have to pick each parameter, perturb it slightly, run a lot of simulations, get outputs, and then you want to numerically approximate like how does the output change with minor variations in the input. And if you want to do a subset of 19 parameters, you also want to see the joint sensitivity to multiple parameters in the input. So you want to slightly change parameter 1, slightly change parameter 2, run a lot of simulations, get the output. So basically the number of simulations you'll run will just explode exponentially. For instance, they had to run like thousands of runs to just do a simple sensitivity analysis. And when the simulators are huge and very expensive, you need huge high performance computing clusters and millions of dollars to do sensitivity analysis. But it's critical because without sensitivity analysis, it's tough to rely on results of a simulator, especially in high risk decision making. So this is something that can be massively accelerated and just transformed with if they built a GradABM instead of an ABM, because of ideas from automatic differentiation. Just to give you a quick recap, we've been doing like backpropagation and reverse mode automatic differentiation is one of the ways in which you can take, let's say, partial derivatives of any variable with respect to any other variable. And the key insight, so I'm assuming like the audience is familiar with reverse mode automatic differentiation or just backpropagation or just automatic differentiation that we've studied in the past. For instance, here is a function f x y z, which is x plus y times c. And I want to take, let's say, the partial derivative with respect to x or y. I can actually build a compute graph which decomposes the relationship between these variables. So I have a node x, I have a node y. I add them to get an intermediate node, which is this property, and I multiply that with z to get my outcome quantity f of x, y, and z. That's how I've decomposed the function. So when I build it as a compute graph, I can now actually take relative partial derivatives between variables very seamlessly. And there is no reuse of quantities. I can just use partial derivatives and the chain rule to compute, let's say, df with respect to any of the quantities x, y, or z, but do it very efficiently. And the key insight is because our simulator is differentiable, we want to use just reverse mode automatic differentiation to do sensitivity analysis. And it specifically works well because reverse mode AD is independent of the number of input parameters, because you just need to backpropagate once throughout the entire compute graph to take any derivatives. For instance, if my outcome is the daily death and input parameters are, let's say, R naught, which is the spread factor of an infection. I naught is something which basically, let's say, the initial infection rate. And I have policy, which is any kind of an intervention that you deployed on the simulation. Let's say it can be a lockdown policy. So parameters of that. I can now take partial derivatives of the death with respect to R naught. So I can see how sensitive was the death to my specific R naught, to the specific parameters of a lockdown policy, and to specific parameters of my initial infection rate. And because it's independent to the number of input parameters, we just need to go once through this entire compute graph, back from death through all these nodes. You can do sensitivity analysis super fast. Because conventionally, by running a lot of simulations, people are trying to numerically approximate a derivative. But because you have the compute graph, we have exact quantities available at every point. And you can use these simulators as, this is the motivating example I started with, that you can use these simulations to evaluate prospective interventions, analyze retrospective decisions, and explore counterfactuals with constraints. So this is the motivating examples I started with, that the differentiable design, the fast simulation, and the ability to do automatic differentiation allows our simulators to do decision making at really large scale. For instance, here we studied the effectiveness of delaying second dose of the COVID vaccine and studied its sensitivity to the efficacy of the first dose of the vaccine, which tends to be a really important variable. So somebody asks, can you really delay second dose of the vaccine? Like, yeah, it depends on how effective the first dose is. And these decisions can be extremely valuable, not just to inform policymaking, because we want to know when will given a vaccine, should we delay the second dose or not? But also it can be used to inform vaccine development and clinical trials, which tend to be an extreme bottleneck. For instance, for a given population, if we know that even if the vaccine is 70% accurate, we can potentially delay second dose to beyond 3 weeks. We could do clinical trials with a lot of varying dosage delay configurations, for instance. And you could use it to ask retrospective decisions, which are demonstrated. You could ask questions like, how effective really were lockdown policies, so that you can analyze retrospective decisions. So what this experiment shows is that we're able to reproduce these field trials entirely in simulation. So I can use this study to understand how effective are policies, but to also design better seroprevalence studies going forward. And you can study sensitivity to a lot of variables. You can study how sensitive was, let's say, infection spread to ethnicity, which is a property of agents in the population. For instance, during the first wave of COVID, we realized that there was more infection among South Asian community than in other communities. And that was an open question. Is it because of socioeconomic indicators, demographic indicators, just comorbidities, some genetic mutation, something like that? And what we eventually realized is, during the first wave, the primary intervention was lockdowns. And South Asians tend to live in multi-generational households. Hence, there is more spread in South Asian community than in other communities, because the only place where infection can spread is through the house. And you can ask these questions by doing these sensitivity analyses. You can understand how infections spread through people in different age demographics. For instance, here we see that infection spread among the 0 to 17-year-old is most sensitive to the school. which makes a lot of sense. And it's extremely insensitive to companies because people don't tend to work at this age group. So we can use these sensitivity analysis as not just to generate insights, but also as like some kind of verification that our simulators actually work well. And again, like questions like you could then design what could we have done differently. So if I want to do this kind of a policy, I know the simulation parameters at each step. So I can pause my simulation at any step along the simulation. I want to see what could an alternate lockdown policy look like. So I stop my simulation at an intermediate step. Now I can do some kind of a Newton step or like just do some kind of optimization on the parameters at that step because I know the objective I'm trying to optimize against. I want to minimize not only public health outcomes, but also economic cost. Get a new set of parameters and simulate again. Now you can do that super fast by using the derivatives to do faster optimization. And finally, I've mostly spoken a lot about epidemiology. It's possible that most of us, a significant proportion of people, are not interested in epidemiology. But agent-based models are used in a lot of fields. And to do that, what we've built now is this platform called AgentTorch, which allows you to build diverse ABMs across domains. You've got an extremely generalizable design where you can scale simulations to millions of agents, a simple Python API, so you don't need to write a lot of C++ code. And it's seamlessly integrated with PyTorch, so you can use their optimization libraries, you can integrate with neural networks. And you can use this to build simulations in biological systems to understand morphogenesis of cells and tissue formation. You can use it in the physical world to do epidemiology, as I described. You can also use it in the digital scenario to study things like opinion dynamics, lock-in behavior of consumers, study misinformation and information dynamics and networks. And with AgentTorch, we've introduced a new model definition. I would encourage you to look at it in the paper just to give some more context on how you can describe a simulator. But the key insight is that any property or function in the entire simulation can easily be learned, either using automatic differentiation or by just replacing it with a neural network and optimizing those parameters. So learnability and fast simulation are like at the core of this design. And we've got a reasonably simple Python API that you can use. Usually, we've got like a config and runner API that you can use to specify and simulate ABMs. We roughly import AgentTorch. You define a config where you specify what are the agents, objects, what are the substeps, all components of the simulation. You instantiate a runner, you initialize the runner, and for each episode, you just need to reset the runner to reinitialize the parameters. You need to run for n steps, and you can just use the output. So the API is designed to be extremely compatible with PyTorch if you want to integrate it with deep neural networks. For instance, you can build hybrid pipelines with deep neural networks and ABMs using AgentTorch that you follow the same specification. But if the runner or the simulator has any parameters you want to learn, runner.parameters directly gives you access to the simulation parameters. And you can define an optimizer with any PyTorch optimizer. And you've just got a couple of extra steps to run. When you train a neural network, you usually, the start of episode, you reset the optimizer. Along with that, you just reset the simulator as well. You can run n steps of the simulation, get the entire trajectory of the simulation, compute any output or loss or metric you want to do, and you can use any of the PyTorch loss functions to just compute a loss on the simulation output. And if you do loss or backward and step the optimizer, you'll end up updating the parameters of the simulation. So easy to integrate it with deep neural networks. And I would encourage you to look at our paper where you can like use this to do supervised learning. You can use it for reinforcement learning. You can chain ABMs with neural networks and like build composable modules, or you can put ABM neural networks inside a specific component of an ABM, or you just want to use gradient descent to optimize parameters of a simulation without any neural networks. There are a lot of configurations that we can explore, and this is something that's available. And yep, and I'm happy to take any questions. Yeah, thank you. And yeah, there are a lot of open problems. So yeah, I just wanted to note there's a lot of open problems that we're always solving, and our group is very interested in these kind of ideas. And we always have a lot of postdoc positions, visiting researcher positions. So if anybody wants to like come work with us, explore some of these similar problems, I'm very happy to chat further. And you can reach out to me at my email.
Thanks a lot, Ayush, for the very engaging talk. Are there any questions?
Yeah, I wanted to ask one thing. Like, you said, like, if instead of optimizing the parameters individually using gradient descent, if simulation parameters, if we instead optimize the parameters of the neural network, with that technique, we were able to reduce the CPU hours, its overall CPU hours to optimize the simulation. So, what was the reason? Like, how did it had such a significant effect that the CPU hours were reduced significantly?
Oh yeah, let me just go back to that slide. Okay. Okay. So I would say it's a combination of two things. First, I feel is that, so when you use a surrogate, you actually have to sample the simulation. You have to generate a lot of samples from the simulator, and you try to fit a model between those samples. Like you put a lot of inputs in the simulation, you generate a lot of outputs, and you fit a model between that. Now, the deal is when you're doing that offline, you need a lot more data points because you don't know what space of the simulation you're exploring, because you don't have like any constraints on like the set of possible simulation parameters you'll have to explore in optimization will be huge. But when you do so gradient descent is a biased estimator. So you start with some estimates and you take always the direction of steepest descent one. Because you're doing it online, the optimization adapts to the space of the simulation that you're exploring. That you don't really want to explore all possible parameter configurations before you get to an answer. And because you're also using a lot of external data, you can further constrain the space of simulation parameters to explore. Does that give you some context? If you do it offline, you don't know what's the set of possible parameters. So you'll generate a lot of data points, then sample the simulator a lot if you do it with like an emulator, and that will take a lot of time to calibrate the parameters because you just have very little prior and not a very biased estimator which is available online. But when you do gradient descent, a lot of heterogeneous data and online optimization, you explore the space of relevant simulation parameters faster. Does that answer your question?
Yeah.
Excuse me, sir.
Yeah.
So can you throw some light on these parameters, theta t and theta p?
Oh yeah, so these can be, okay, for this specific instance, let me show you. Just, sorry, I'm sorry, I think I'm running through slides. Okay, so these parameters, for instance, theta t are basically, let's say, a bunch of mechanistic, epidemiologically relevant variables that guide transmission of new infections. For instance, COVID is an age-stratified infection, for instance. So transmission of COVID is directly proportional to only three variables. It depends upon R naught, which is basically the scale factor of the infection, like how fast is this infection spreading. It depends upon the susceptibility of each individual. Since susceptibility depends upon age in terms of COVID, and it also depends upon the transmissibility of an individual based on how many days they've been infected. So if I want to figure out what's the probability that this interaction will lead to an infection, it's some linear function of what's the R naught, which is how fast is this infection spreading, what's the susceptibility of this individual, which depends on the agent's age, and what's the transmissibility of the infected, which depends upon number of days they have been infected. So theta t is basically three parameters here. It's the R naught, its susceptibility varying with age, which is like some kind of a genomic quantity that you can compute. And there is also a transmissibility varying with number of days of infection. For instance, we had some kind of like beta distribution curves where like in transmissibility first goes up and then goes down towards the end. If your infection lasts like 14 days, for instance. So these are the transmission parameters, which can be used to describe a interpretable transmission model that most epidemiologists use. And progression parameters are telling you how fast are you moving through your individual life cycle. Like you want to go from S to E to I to R to M. So one parameter this has is the mortality rate. That if an individual is in the infected state I, what's the probability that they'll end up recovering versus probability that they'll end up dying. So you parameterize that with the mortality rate. And you also have a parameter called a generation time, which basically tells you the generation time of a virus is the time it takes for an average individual in the population to go from S to E and E to I. It's basically how quickly will a new generation of infections be produced in the population. So theta P is basically the generation time and the mortality rate. And theta T is R naught age susceptibility and time-based transmissibility. Does that make sense?
Yeah, thank you.
Are there any more questions?
Yeah, I wanted to ask the results that you shared, where you are comparing your this agent-based module with June. What kind of a GPU was used? As in, because the difference in number of parts is quite huge. So, what kind of hardware and data was it used?
Okay, so for the comparison, we used exactly the same infrastructure. So for all these experiments, we use like a single 24 gig GPU. Like you don't, which is like in today's time, not the most expensive to acquire. You can just get a single GPU. And we use the same hardware for both, the exact same data for both, the exact same simulation logic and scope for both experiments. But it's like a single 24 GB GPU.
Yeah, thank you.
And yeah, actually, we have a few more future results, which I haven't included here, where you can actually now scale, we've scaled up to like 60 million agents, which is like the entire population of the UK. And we can even calibrate that on a single GPU, like 24 GB, using like a bunch more engineering optimizations in how you compute gradients. So I think we can technically scale simulations to like entire countries, entire continents for extremely low cost. Like you don't need like millions of dollars to run this. Unlike how you might need for LLMs, you don't need that. Maybe like a few $100 is good enough.
Okay, yeah, thank you.
I have a question. You had mentioned in a footnote on one of the slides about Blackbird. So can you just?
Oh yeah. So that's not my project, but it's like a really cool project by one of my collaborators, where they've basically built this general pipeline which allows you to, if you want to, let's say you have a differentiable simulator and you want to calibrate posteriors, they've got like a bunch of really cool toolkits to where you can just directly plug in your simulator. You need to build a differentiable simulator separately, but they'll give you like all kinds of support to estimate posteriors, to generalize variational inference. You want to use in a way, like if you want to estimate posteriors over simulation parameters, it's like a really good library, and they've recently built it. So I think it's like cool to use if you want to check it out.
So it assumes the simulator is available like a black box.
It assumes that you need to have active simulation. This is like he's one of my collaborators and now who built this.
Okay.
And yeah, so they've got like a bunch of really good test cases, but yeah, they assume that the simulator is accessible. For instance, here they're using a random walk simulator. Instead of this, if you want to build your own simulator, you'll have to plug it in. You'll have to make sure it's differentiable beforehand. But yeah, they're mostly it's not at the scale of agent-based models at the moment. But it's pretty good if you have, even if you have like, let's say some simple ODE models, or you have like more simplistic simulations. The focus is more on having like a good library to do parameter estimation and posterior calibration on simulations.
Okay, great. Thanks.
But yeah, I mean, just to reiterate, it's not my project, but it's just a project I like. So I thought if you want to ever think of this, maybe this is a cool thing to check out.
Thanks, Ayush. So I'll invite Gargi to take over. Gargi, are you there?
Yes. Okay, so yeah, so I would like to thank Mr. Ayush Chopra for this informative presentation on learning to simulate millions of agents. On behalf of ACM Goa Professional Chapter, I'm grateful for your time in presenting this interesting field of agent-based models. Thank you once again. If you
Yeah,
do not
thanks
have
a lot for having me.
Yeah, if you do not have any more questions, then we can leave the chat.
Yeah, thanks everyone for joining. I'd just like to mention that we have a bunch of talks lined up. At least once every month is what we are planning, and we have an offline event, which is a networking event in Goa planned in September. So looking forward to seeing you all there. And if you want to be notified of these talks, please register on the ACM Goa webpage. We have Google form there. Yeah, so thanks all, and thank you Ayush for giving the very interesting talk.
Yeah, thanks a lot for having me over. Yeah, thank you. And yeah, please feel free to reach out if you have any questions. I'm happy to chat on this. Thank you.
Great.
Okay. Talk to you soon. Bye. Take care.
Thanks everyone. Bye.